All right, so I'm Alex Birch. I work here at Scott Logic, and this is one of my personal projects. So my background, I did a lot of game development as a kid, and in terms of open source, when I see things that inspire me, I like to make my own version. I like to make things better, and this is a story of one such project. So I'll show you the game I was trying to make, and I'll then show how that relates to open source, like the project I made and shared, so that you can make games like it. Where's the mouse cursor? Okay, so I think I'll skip that. Keyboard. Okay, so did anyone here play Mario Galaxy? This isn't the game I made. Someone else made that in Japan. So I really like this idea of a platformer that was physics-based, and that gravity didn't just go down; it went everywhere. So I tried to make my own one in 2D. So first I tried doing it with maths, with vector projection. You just work out which direction you want to point. That has trouble with concave surfaces, and it still doesn't solve the problem of how about inertia, how about collision reaction. You can solve the problem of how do you go between planets if you instead calculate gravity and inverse square and then sum them. But again, still no collision, still no inertia. You can slap some paint on it, but there's problems. So this is with like kind of fake collision detection reaction. You just look at the pixels and then there's no bouncing, there's no anything. So it is very limited physicality. So how about we get a physics engine? Did anyone here play any of these games? Yeah, so there's Tiny Wings, Angry Birds, Cut the Rope, Rolando, Shovel Knight. All of these games are famous uses of the Box2D physics engine, which is open source, zlib licensed, and now MIT licensed. And Box2D is already on the web. It was so that was my first try using Box2D.js. The problem with Box2D.js is it's a bit out of date. It adapts Box2D, the physics engine, as of 2014, but it misses out on all of the 2020 updates. It misses out on rope physics. So that was my attempt to simulate rope physics like a decade ago. It's not ready for the modern web because there's 1,500 functions and it doesn't tell you what they are. You need TypeScript bindings if you want to use Box2D. So can we modernize this? I'd like the latest Box2D, and I'd like TypeScript declarations. So first of all, Box2D is written in C++. It'll have classes like this one. So that's how vectors work. You've got floating point numbers. You've got x and y. It's got methods. That's written in C++. How do we invoke this from JavaScript? So you compile it to WebAssembly, which is on the right. You've got assembly instructions. So you have a function named vector2set. It has 3 parameters actually, because the first one is a pointer to the instance of the vector that you constructed. And then you've got x and y, they're floating point numbers. It's a virtual register machine. Is that correct, Colin? Stack-based virtual machine. Okay. So you put on the stack the pointer to the object and y, and it will store it 4 bytes away from where the object starts. And then you put then again you put the pointer to the object on your stack and x, and you store it at where the object starts. So that's what it looks like when you compile the C++ to WebAssembly. Now the question is, how do we invoke that from JavaScript? What is the calling convention? So we like to use the C application binary interface. Everyone's agreed this is a great foreign function interface. So you have this bridge. You have this glue code where if you want to invoke the C++ method set, you would create a C function vector2 set. You would take a pointer to the object instance and all the parameters, and you would delegate. You would forward the call to the C++ function. This visibility modifier tells the linker not to get rid of unused code and to make it a public symbol. So we're going to need to make 1,500 of these. Let's say we compiled that program back there, and we wanted to invoke it from JavaScript. What would that code look like? You've got your WebAssembly. You compiled it with Clang or Emscripten, and you download the WASM bytecode. It's already parsed. You execute it, and you pluck out all of the symbols, the public symbols that are exported from it. You've got the method that you exposed, and you've got the memory, which is just a long line of zeros. And then you say, at 0 in memory, I want to invoke that function. That 0 is my vector. I want you to throw some 1s onto it. X and Y will be 1 and 1. And then, again from JavaScript, we can get a floating point view over the heap. We say, show me the first and second floating point numbers on our heap. And they'll be X and Y. So this is a very, very manual way to invoke C++ from JavaScript. How do we scale this up? And you notice there, this was not type safe. There was no documentation. How did we know this method existed? Well, we remembered that we put it there. That's not good enough. So now, TypeScript declarations. So we do an unsafe cast. We say that the program you've executed will not be just a boring old WebAssembly source. It'll be a subclass of source. It'll have a subclass of instance, and the exports will be subclass of exports. And we will say, you can expect to find this method on that WebAssembly instance. How do we do 1,500 of these? So we need a language specification for saying what functions exist. So we use WebIDL. This is a format for declaring bindings. Our C++ class on the left can be bound to by this WebIDL description of it. We say there will be a class named vector2. It'll have a public no-args constructor. It'll have 2 floating point attributes and 1 void method. And Emscripten's WebIDL binder will take this description and produce that glue code that we made earlier, that C implementation for us. So this can be auto-generated now. We also get the constructor, for example. By the way, this isn't a very good constructor. New seed control of how is memory allocated. So it uses dlmalloc if using Emscripten, but if you wanted to say, I want to use a small block allocator, you could use placement new. You'd have to write your own binder for that. So, okay, so Emscripten can create that C interface for us. Can it create the JavaScript for us? Yes, and in fact, if we wanted a really idiomatic JavaScript interface, we would use classes. We wouldn't use a bunch of loose methods. We wouldn't ask you to pass a pointer in. So, what if we wanted to construct a JavaScript vector? We would do it like this. This is a fun thing. So, how do we do those attributes? We said, okay, so I'm in JavaScript. I want to construct an instance of a vector. When that happens, it will use, it will invoke that vector2 constructor that was exported via WebAssembly. It'll allocate memory for it, and a pointer will be returned. This will be hidden and remembered by a class. If we want to invoke, if we want to expose to our JavaScript callers a set method, we can invoke WebAssembly set on our pointer. It's a private property, but we've remembered it, and pass the x and y to WebAssembly. The attributes are fun because we don't even need a method at all to look those up on the WebAssembly heap. We can use maths. We can use pointer arithmetic. We can say we know the vector starts at the pointer that we were given, and we know that x is the first floating point number there, and y is the floating point number after it. We just add 1 to the pointer. So that would be the very fastest way to provide attribute getters in JavaScript, just direct heap lookup. But you could also make mscripten actually generates functions for these. And I think it doesn't make a difference at the end of the day. The JIT will inline them across language boundaries, so you'll get the same result either way. So we were able to make the C glue code with from the WebIDL description. We were able to make the JavaScript abstraction from WebIDL. Can we make TypeScript declarations from WebIDL? Yes. So that JavaScript class we made. You can just as easily imagine a TypeScript class. The important part is this, but there's the details of how do you pull this out of an mscripten factory. There's a promise and everything. Let's focus on how do we programmatically make one of these. This mscripten does not give you for free. It's the first thing that our toolchain doesn't give us. So I had to invent a way to do this for Box2D WASM, my WebAssembly project. So if you go on, there's a website, TypeScript AST Viewer, where you can type in arbitrary TypeScript, such as declare module Box2D WASM, and the website will tell you how would you use the TypeScript compiler API to generate that same TypeScript program. So declare module, create module declaration. Export class, create class declaration. It'll tell you what to type into your program to make that program. You may have noticed TypeScript is just a Node.js library, and you can say import TypeScript, and it has a bunch of functions for making TypeScript programs. So now that we know we can use TypeScript to make TypeScript, let's parse that WebIDL declaration using an off-the-shelf WebIDL parser. Let's iterate through every through every AST node, and emit TypeScript classes using the TypeScript compiler APIs. The important thing is we make an array of TypeScript statements. And 1,500 bindings later, you get something like this. So compared to the earlier experiments I was showing you, we have collision detection and reaction. We have gravity calculated. We actually have curved gravity. So you use a Bezier curve, you work out the closest point, and you create inertia towards it. We've got fighting gravity sources. So two spheres, they each exert their own gravity. We sum it. And we have priority gravity. So if you want to transition from curved gravity to line gravity, we have a precedence list. This is how it's implemented in Mario Galaxy, and I did that in 2D as well. You can slap some paint on it, and it looks like this. The sprites aren't aligned perfectly, so it doesn't. The video is longer than that. Whatever. So the next chapter is after we got parity with the original Box2D.js project. What happens next? Fluid simulation. So this is where the kind of open source story starts. People hear about your project and they want to use it in different ways. They have different ideas for it. Someone, Dan Brickley, who works at Google Open Source, asked, hey, could you do exactly the same thing for Liquid Fun? Liquid Fun is a Google fork of Box2D that adds fluid simulation and soft body dynamics to Box2D. And so you check out the project, Liquid Fun, what happened with it? And there are people asking why there are no more releases of this thing. Since 2014, it's been abandoned. And they say, we ran out of time, it's too hard. Why is it too hard? Because in 2013, when they began the project, they forked from old Box2D. They created an SVN repository. They put everything into a different folder. They used a different style of line ending. And because they're on old Box2D, all the file names are different, everything's in different folders, the license is different. Liquid Fun used different data types. They put all the source in a different folder. Everything about these repositories was irreconcilably diverged. So, if there's 6 years of Box2D updates in mainline Box2D that you want to give back to Liquid Fun, how do you salvage that? 1 week later, I'd rebased the Liquid Fun project onto mainline Box2D, and I'd run it through all my WebAssembly stuff so that we have WebAssembly and TypeScript bindings. And one person was happy. And now we have... this is where I want to use the Mac. Right. And now we have fluids. And that's only the start, really. So other people are also using the project, and they're like, I actually have a game in production that uses a Box2D game engine. I'd like to switch to your WebAssembly version to make it faster. The reason I was... So he wasn't using Box2D.js. He was using like Box2D TS. There was like a TypeScript native port. It wasn't performant, but it had TypeScript. This was the first way to get performance and TypeScript declarations. So, and he's gone to production, and you may recognize he implemented a feature from Getting Over It, the PC game. And it was really nice to see my game engine used to make something I'd heard of or something that's big. It actually helped someone. And in particular, this homage feature, the guy in a cauldron using a hammer to navigate a world. The way he told me about this was he opened an issue asking, how do I get access to private properties of prismatic joints? No explanation. And like, if you help with that, you enable people to make cool parodies like this. And as a game developer, he told me more things that can be done with the game engine. He said, he said he's heard of this kind of stuff before, and what people usually did with Liquid Fun was render all those dots as water. They join the fluid using OpenGL shaders, and having never done graphics programming before, I had no idea what was involved in that. But like he as a game developer had good relationship with, I think, Cocos2D. So he was able to explain how to get the graphics to look like water. These videos played better on the Mac. So, and he drew my attention to Google's presentation of Liquid Fun, where they had an eye candy demo where they drew really good water. And there's another shader. Yeah. So the left one is it uses information from time. You store store a few frames of buffer and refer to them when you draw your next graphic. And the right one is it doesn't do that. So because that was OpenGL and there's a WebGL standard, you're able to more or less without changes copy that OpenGL code and just throw it into a web page. And this was kind of the culmination. This demo I made combined all of these techniques and used fluid, used orbital physics, and used rendered water. That's actually... Oh yeah, there's only one more thing left. There's performance. How do we make a performant demo? How do you go 60 frames per second without dropping any frames? How do you get rid of stuttering? There's actually, I did the other shader as well, didn't I? So you can... Yeah, so that's a temporal blend. It remembers like a second of stuff it's drawn and blends it. So how do we make a fast demo? So to draw a graphic at 60 frames per second, you have to compute a time step every 16 milliseconds, and the physics takes 5 milliseconds unless your computer's overheating, which it is. So that gives you about 10 milliseconds, 11 to draw all the physics that you've calculated. It takes less than 1 millisecond to send the vertex buffers to the GPU, and I don't know how long the GPU takes to draw it, but drawing can be fast. But your main enemy here is the garbage collector. If there is a large GC pause, then you lose JavaScript execution for a few milliseconds. Is absolutely enough to cause stuttering, and that will impact your physics calculations. If you're saying physics time and render time are the same thing. So how do you stop garbage collection? You stop creating garbage. Avoid heap allocation. If you need a structure, reuse it. Don't make objects, don't make arrays, don't new, and don't use functional programming. I think at this point you're saying, well, hang on, that's not JavaScript anymore. Yes? They've given us some nice techniques like typed arrays that allow... JavaScript arrays, they're associative arrays, they're dictionaries, they're sparse in memory, except for optimizations, like small one. If you want guarantees about is it just going to be a line of memory, use a typed array. And like numbers in JavaScript are like double precision floating point numbers. What if you actually want loads of bytes close together to be integers? Again, typed arrays. And draw everything via WebGL so that you can... the graphics card is much faster drawing 1,000 things than your CPU is. Your graphics card has thousands of stream processors. And that's everything. Any questions?
That was brilliant. I'm just going to point out one thing. How do you rebase 6 years of code 1 week later? Alex definitely is a hacker. Any questions for Alex? I've got one, of course. So you mentioned you're fighting garbage collector. So you're using WebAssembly for your physics engine, and WebAssembly doesn't have a garbage collector. So I'm assuming the garbage collection is within your sort of model universe. Have you considered doing the modeling in WebAssembly and then basically just pushing buffers straight into WebGL? You know, effectively getting rid of JavaScript?
No. Yeah, actually, assembly script would have been a really good way to do all of the parsing vertex buffers to WebGL. That's a good idea.
Yeah, I expect to see it next week. Any other questions? You're all suitably baffled. I think it was a fantastic talk. Thanks a lot, Alex. I'll move to one side to let you move past.